All right. We'll get started. Welcome, everyone. This is the panel comparing different privacy-enhancing technologies, PETs. I'm Derek, on the investment team at Variant Fund. We're an early-stage crypto VC that invests against a thesis called the ownership economy, basically funding user-owned and controlled networks. As part of that, look really across the entire investment landscape. One important category there is new privacy infrastructure. There's a lot of interesting developments happening at the cutting edge there. So excited for the panel today. Would love to turn over to each of our panelists if they could talk a little bit about themselves, the project, and then importantly, the technologies it employs. Start with Rob.
Cool. GM, everyone. I am Aztec. This is an FHE Summit, but Aztec does ZK. We are a privacy-preserving layer 2 on Ethereum. We have both a private chain, private functions, but we also have public functions and public state. And that's because hot take alert, think a complete private chain is actually not as useful as people think. You need some aspects of public side too, for great things like DeFi, for example. And I'm sure we'll go into that later. But yeah, it's all for now.
Good afternoon, everyone. My name is Zheng Leong. I'm the co-founder of Automata Network. So we actually kind of like deal with everything related to TEEs, actually. So similar, not FHE, TEE. But like one of the things that we are trying to do really is to kind of like bring trust, like machine trust into our entire Web3 ecosystem. You can think of it as a machine attestation layer that is built by humans. So the idea is that there are some kind of like hardware root of trust that we can rely upon, and then from this hardware root of trust, we can perform some interesting things like data provenance or like integrity of the computations being done. So, yeah.
Hi, everyone. It's me again. So I'm Remy, founder of Inco. So what we're building is a blockchain layer that can extend other blockchains to support confidential compute. And so the underlying confidential compute cryptography we're utilizing is FHE. But I know I talk a lot about FHE, but in reality, we also use MPC for decryption and then ZK for proving ciphertext that the ciphertext is not malformed, and also the knowledge plaintext. So I know I talk a lot about FHE, but we do use other cryptographies as well to make this overall system robust.
Awesome. This is a bit of a high-level question, but we'd love to start off with each of your kind of like individual theses on privacy, why you're so excited about the category, why you're building in it, looking forward, what you're most excited about. A bit generic, obviously, for an FHE Summit, but I find that every project approaches it from a different perspective, which I find interesting. Why don't we kick off with Rahul?
Yeah, why privacy? Well, I could give the easy answer of like, you look at blockchains today, and it's a regression of what we have in the real world. I wouldn't say in like Web 2 we have privacy, but we have like privacy with respect to other users. So let's call it user privacy. But you don't have operator privacy, right? Like your bank or whatever in the middle who's there knows everything. And in blockchains we regressed. We have everyone knows everything. So if you build like, I don't know, some on-chain social app or something, it's objectively worse than Facebook, because at least in Facebook, they decide what to do with your data. In blockchains, like any random insurance company can just see it and charge you based on random tweets that you've posted on chain. That's the easy answer. The harder answer is like, I think one of the ways I look at blockchains is a way to advance cryptography. If everything else fails, I'll be happy if we have improved cryptography that is used by Web 2, for example. By being extremely like cyberpunk about what we mean by privacy, which is like absolutely like privacy from everyone, including the operator, having extreme like censorship resistance, we get to work on really hard cryptography problems. We get to improve ZK. Some of these might maybe be used for like FHE research. We get to like have impact on TEEs as well. And I think like you see secondary, tertiary effects. For example, like Apple now, every iPhone 16 uses FHE for certain things. All of iPhone 16 also uses TEEs now at scale. OpenAI has a privacy division just researching on ZK and FHE. So like even if all of this blockchain stuff fails, we get big tech to do some work on privacy. That's a big one.
Yeah, my thought on privacy is, so for me, it has always bothered me that everything is transparent on existing blockchains. And to me, blockchain is really the value layer. So payments being the killer use case here. And just like, yeah, if you imagine bringing in 1 billion people to the blockchain system today, it would actually be social chaos. Like imagine your neighbor knowing how much money you have on chain, your friends, your family, you can put yourself at risk, right? You can have bad actors really like scheming and kidnapping you because of it, right? It just doesn't quite make sense socially to have everything very transparent. I think it would actually create a lot of social chaos, especially if you think about something as simple as payroll. Yeah, just knowing that, let's say your peer makes more money, or how much your boss is making, it would definitely create a lot of internal conflicts. I don't think as a species we're ready to have that level of transparency. So to me, yeah, like basic privacy on chain is a necessity for mass adoption. Because yeah, the reality is if you put billions of people on chain today, I think there would be quite a bit of weird social dynamics happening, and I don't think people are ready for that. And so that's my biggest thing on privacy. Yeah.
I totally agree. Like recently, I've just signed up for a kind of like crypto credit card where all your transactions will actually be like charged to your what's it called, on-chain kind of like wallet. And after using it for a while, I came to realize that I might not actually continue using it. Why? Because you can actually see each of the individual transactions that I've made. Like maybe I spent like $4.60. Now the thing is, people don't know where I spent it from, but the numbers actually reveal certain things. Of course, we can if we have like FHE and stuff like that, maybe it can make things a lot better. But after listening to my two fellow panelists, I kind of like have a new thought, which is other than from the user perspective, what is privacy good for? I think privacy is good for businesses also, because if you think about it, in like I know everyone hates regulation, but regulation is going to exist, and a lot of the regulation that we experience nowadays, there's a very heavy privacy emphasis in it, especially in Europe. So if you're a business that wants to do that wants to do business in Europe, for example, you have to deal with GDPR, for example. You have to fulfill certain regulatory demands. And this is where PETs would come into play, because it allows companies to actually tick those boxes or fulfill those demands from regulators. Yeah.
A lot of that definitely resonates. I mean, a quick way that we usually use to sum it up is it effectively expands the design space of what's possible with crypto. Like allows you to create apps that just like frankly aren't really possible, don't really make that much sense right now. And with that, in terms of how you exactly build some of those apps, we'd love if everyone could go through their individual PET. We have like roughly ZK, trusted hardware, FHE, talk about like key trade-offs, an overview of it, and then we'll dive in deeper from there.
So like trade-offs of ZK, for example. Okay. ZK is like more of a verifiable technology, right? So you do something and then you verify to me that whatever you did was what I expected you to do. That means if you try to use it for privacy, that means a user has to execute everything and then they need to create a client-side proof and then send that to your validator. This is quite different to traditional blockchains where like the sequencer does everything for you. This is great in one interesting way, wherein your fees are actually lower. Because in public blockchains, there are a lot of DOS vectors, right? The sequencer needs to be made sure that they're paid enough to do work for you. But here, because you're doing all the work, the sequencer doesn't really do much. Like, okay, we're in L2, so all they do is like they take all of your new states that was created or destroyed, and they post that to L1. That's pretty easy to figure out what to do, really easy to meter. The trade-offs are, okay, so users have to do proofs. In blockchains, in Web2, we're not used to this mindset of users having to do work. So that's one thing. It also means you can't use co-processors that easily in the way you can with FHE, because you're delegating who does work so they know what the private inputs to your proof was, what you want to do. And the final one is, and this is true for FHE as well, is you can't have shared private state. So what I mean by that is like consider Aave, right? Where your borrower rate inherently depends on what he does, what I do, what he does, and so on. So like if all of us were borrowing completely privately, you do not know what the utilization is of the market, and now you don't know how much yield to give to me. And so some things have to be public then. And so there you come into this really fun trade-off space of like, okay, what do you want to keep private and for how long you want to keep private? By what you want to keep private, is it just the user address? Is it just the balances? Is it also like the functions that you call and the contracts you interact with? By when, I mean like MEV world really loves keeping things private until the sequencer has to create the block, right? So you only need privacy for like 10 seconds until the block is committed and finalized. Maybe you want privacy until like the full L1 is finalized, so like 6 blocks of L1. Or maybe you want privacy till eternity or until your keys are leaked. And that is a trade-off that exists for the app developers, so things become much more complex for them as well.
So I think Rahul did a real good job explaining the details. So maybe I'll kind of like answer in 2 parts. The first part, actually the amount of computation that is needed for all the different cryptographic gadgets and primitives. So for example, like FHE, MPC, ZK proofs, all these are extremely computationally intensive. Like we have been saying how like 2025 is going to be the year of real-time proofs. Yes, we can have real-time proof, but your real-time proof hardware is going to take up like what, 1,000 watts? You can't stick that into your mobile phone. It's just physically impossible to do the computation unless we come up with some really fancy, very clever math that allows us to do that, but currently it's not possible. On the but what you get really is that you get this extremely high level of guarantees, like theoretic guarantees that you get from all these different schemes. On the other hand, for TEEs, you actually have a very, very, very cheap cryptographic kind of like mechanism or gadget for you to achieve a relatively okay or high level of confidence. Like, of course, it's lower than, for example, ZK proofs or say FHE computation on encrypted data, right? But what you have is it's cheap. You actually have a TE in all your phones now, like whether you are using Android or iOS. And I think it can be used like in conjunction with all the different kinds of like gadgets that we have. The other aspect is actually more on the business or regulatory side of things. If we look at it, out of all these technologies, TE is the kind of like oldest one. Like FHE, ZK, MPC, it's relatively newish. Like the papers would be like from 30 years ago, yes, but there isn't really a kind of like industry accepted implementation or like standardization of all these technologies. TEs, on the other hand, is relatively accepted by like regulators, governments, Web2 companies. As a result, if you speak to, for example, the CEO of a big company, or if you need to like talk to regulators, I guess they would be actually more acceptable of TE compared to all the different cryptographic gadgets. The opposite is true for Web3, actually. People are more excited about all these new cryptographic mechanisms and less so on TE. But if we look at the kind of like the traditional world, it's actually the other way around, because people can understand TE. It's easier for regulators to understand like where the boundaries are. There are big companies behind the TE implementations like Intel and AMD that governments can actually like find them, or if something bad truly happens. So yeah.
I think all these PETs have very unique strengths that might be very suitable for specific use cases. For example, like I think ZK, if you want to build anonymity, I think ZK is better than FHE. The reason why is with FHE, everything happens on-chain. So if you want to build some kind of mixer or anything like that, it just becomes very costly because you have to match everything on-chain. But ZK matching is a lot more efficient off-chain, right? And anonymity is actually quite necessary even for payments, right? So if I visited a doctor, that information needs to be private, right? Because that can have repercussions later on if you want to find a job or things like that, right? People could discriminate you. If I want to do political donation, anonymity is necessary, right? Because you don't necessarily want to show who you donate to, right? So I do think ZK does have its own unique strength, and so it is quite complementary. On the T side, my thoughts on that is that I think it's very good for short-term privacy, because I think T historically has had this controversy of like, okay, someone can hack it, someone can leak information, and so we're in a very unique industry where everyone's trying to hack you, right? Like your developers, your users, the governments, like, because it's a public blockchain, right? Everyone's gonna try to steal your money and like hack you, right? And so I do think for long-term privacy, you probably want something that's more like MPC, FHE based. And short-term privacy, maybe like for like an MEV protection or like, let's say poker game where the duration of the game is like 5 minutes. And T is okay, because your risk is really during the duration of the usage. And so I do think T's have a lot of uniqueness that could be very suitable for specific use cases. And so yeah, ultimately I do think from that angle, I think depending on what use case, you probably want to select the right tool that's based from a performance, cost, and like everything as a whole. That would be my thoughts on that. And yeah, Yannick, welcome.
We have a new friend. Yeah.
Thanks
Why
a
don't you
lot.
introduce yourself? And then last question was kind of an overview. I mean, in this case of MPC, key trade-offs.
Yeah, sure. So hi everyone, I'm Yannick from Arcium, and we are doing confidential computing using MPC. So what I got from your answer is basically, yeah, I would put it in a similar way. So we're doing MPC, and MPC makes use of homomorphic encryption, not fully homomorphic encryption, but homomorphic encryption in the way that we use MPC. So a subset of the operation are performed homomorphically, and for other operations we make use of so-called pre-processing and beaver triples. I think one of the main important aspects for me really is that the TEEs for me offer this sort of constant trust assumption. So it's just I trust the security of this hardware, and it's sort of this constant trust assumption. With MPC, we sort of have the scalable trust assumption, because we, for example, at Arcium are operating in the dishonest majority setting, so it's 1 out of n as the trust assumption. Yeah, I think that's also an intersection where different systems can be combined, different architectures. Different architectures can even be pipelined. So I think there's room for different use cases using different technologies. I think one of the main reasons why we're using MPC really is efficiency, and also being able to support things like oblivious data structures, oblivious sorting algorithms. So in order to allow for enormously sized data structures, basically to access them from a confidential computing environment, to basically have pattern encryption, pattern hiding for accessing those kind of data structures. MPC is sort of this logical choice, and especially when it then comes to more complex operations. So for example, we've started doing a lot of stuff in the machine learning space as well. We've just last week announced our acquisition of our largest Web2 competitor, who've been building MPC protocols for the last 8 years, and performing tensor operations, performing real number operations in a cryptographically constrained environment adds enough overhead. So I feel like there's different kinds of trade-offs. And for MPC, I think trust model and efficiency requirement wise, we're in this sweet spot right now.
Thanks, everyone. So we heard some of the key trade-offs, and importantly, some of those are kind of like long-term and chronic, but at the same time, some are just short-term and really just sort of these like research compute barriers. We'd love to hear a little bit about, like, for each PET, what's kind of the like most pressing issue right now that you think can improve over the next few years. Why don't we start with Yannick?
So I feel like all TEs, and I just arrived late because I had a panel with some folks from Jensen talking about federated learning and confidential AI, and performance is what all of us worry about, I feel like, regardless of the specific kind of technology that we're using. So, and the different kind of technologies actually then require different kind of optimization. So it's optimizations on the hardware level, but it's also optimizations on a cryptographic protocol level, on a communication level. So I feel like for us specifically, with the kind of MPC that we are using, we're doing a lot of hardware acceleration actually to make local operations more efficient. We are looking at new kinds of encryption schemes to allow for more minimized ciphertext to be stored on chain. Yeah, but in general, what we are also working on is packing multiple communication rounds into smaller communication rounds, and to be able to reduce this one constraint that we with MPC unfortunately still have to work with, which is communication. Yeah.
I think hardware acceleration is probably one for everyone, I would think. Yes, let's do ones in addition to that. Any additional commentary you have?
Hardware acceleration is a fun one because like you can't, before you commit to doing this project, you don't actually know how much improvement you'll get because it's so based on like what you're doing. Okay, so things improvement needed in ZK. So people mean two different things when they talk about ZK, which will change my answer. If you mean the way ZK Sync uses ZK, which is not ZK, but like validity proofs, verifiable computation, there all people care about is like cheaper verification on EVM chains. That's literally it. If you care about ZK from the privacy enhancing technology angle, then you have, I could give the easy answer like, okay, yeah, cryptography needs improvements, blah, blah, but you did a great job of explaining the rough things that change. I'll give like secondary or third order effects that need to improve. One is this really fun problem called note discovery, which is in a privacy chain, if you get a note, how do you even discover the note? In a public chain, there's not a problem because you have some node that just adds it to your balance. You can query from Infura or Etherscan and see that you got a new transaction with some money. What do you do in private? Like I wouldn't even know that like some farmer has sent me tokens unless I brute force the entire state of the chain. This, by the way, if it might sound crazy, it's exactly what Zcash do. It's also what Penumbra does. It's also what Alio does. So all of the current private ZK-based privacy chains, they all do this brute force thing where they brute force the entire state of the chain to figure out what's yours. Because everything's encrypted, you try one by one, which is yours. Real solutions for that are things like you can tag the note when you're creating this log, going like, hey, this is for me, and then you just query your tags. So brute forcing tags would be much quicker than brute forcing all of the notes, and then you decrypt. You could go one step further and do like a form of homomorphic encryption called oblivious message retrieval and private set intersection, where you have a list of things you want. The node obviously has the entire state of the chain, and you kind of want to figure out what things match, what is the intersection of these two sets privately, without the node knowing that you have these things. And like those things obviously have huge overheads. They don't work well today. Hopefully they'll change. The biggest problem of that is actually not the cryptography side, is the bandwidth side. Proof sizes will go smaller. Everything will become faster and cheaper. That's not an issue. The issue is bandwidth. Bandwidth for most countries will probably not change by much in the next 5 years. And so like how do you reduce the bandwidth optimizations? How do you do that? That's a very hard problem. The other secondary tertiary effect is like decentralization. No L2s today have decentralized. How do you actually decentralize things? How do you make upgrades happen without a multisig? So those are like secondary tertiary problems of like once you do any privacy chain.
Okay, so like, what can we do with TEs, right? Like, how can we improve TEs? One of the things that we can improve on TEs is really to have like secure, open TE hardware. Like, this is something that is lacking. It's even lacking in non-TE hardware. Like today, the laptops that you have, the computers that you're running your geth node or your ref node, your verifiers, we actually don't know if it's backdoored or not, like sadly. Anywhere within the entire supply chain, there can be people that would maliciously add in certain backdoors to your machines, and you're none the wiser. There are work like that is being done on how we can mitigate this risk, but the entire hardware space is really this kind of like very traditional, very closed source, very proprietary, with a lot of like trade secrets and NDAs. So you won't have a open platform. And this is one of the biggest problem for TEs, because one of the biggest complaints about TEs is that it's a black box that is built by Intel or AMD or whoever, and I can't verify it, I don't trust it. If we can actually have a kind of like, we can imagine a world where we have this open design, we have an open manufacturing process. The fabs actually publish information about like the diagrams and stuff like that. We can all dream. And what we can do is after the manufacturing, during the assembly, we can perform like cut and choose type of verification where we destructively validate that the chips are indeed, we randomly kind of like pick some chips and then validate that they are indeed what we think the chips are, right? Then, and then after all these are done, we need to kind of like fuse the secret into the chip. How do we know that Intel is not keeping the private keys of the CPU that is being sent to you? If we can have a distributed open way of performing this embedding of the secrets into the hardware, then everyone can have more trust. It's just like the DKG, the DKG ceremonies that we have now. So I think. You mean the trusted setup? Yes, sorry, the trusted setup. Yes. So basically, moving forward like this, if we can actually achieve this, then TEs would become really powerful because we can have the verifiability. It is basically not controlled by a central entity, and it's like cheap and fast. Like it's really efficient. So this is something that I think anyone who is interested in TEs should like look into.
And there is an initiative around that, right? Open
Yes.
TE. Okay, yeah, that's quite exciting.
Yep.
Yeah. So on the FHE side, I'm sure everyone's aware, the biggest complaint is that it's very slow, right? But the good news is FHE is compute bound. So what I mean by this is, if you have a system that's, let's say, an MPC, your bottleneck ultimately is networking, right? You can't go faster than the speed of light. With FHE, because it's compute bound, you just have to throw hardware at it, right? Better hardware. If you look at Moore's law on, hardware developments, it will get faster. Like, for example, if you look at the Bitcoin ASICs, the first generation that came out, heavily accelerated the mining, but these things got a lot faster, a lot cheaper over time, and you can expect the same thing for both ZK hardware acceleration, and also FHE hardware acceleration. And so because this is only compute bound, it's very subtle, and we saw this with Michael's presentation today. If you do a FHE multiplication on a 64 bits, it would take something like 400 milliseconds on the CPU, but with the VPU, it's roughly 43 milliseconds, right? So over time, you would probably get to sub 10 milliseconds into a single digit millisecond. And so the path of scaling FHE is really just using hardware at this point. And the second thing to note is you can also horizontally scale. So in our context, we use FHE for smart contract computes. So if the states don't conflict, you can just load balance, right? You can just throw a different hardware. With a single GPU today, we can do 19 TPS over a confidential ERC20 transfer, which is a FHE addition, subtraction, comparison, and a multiplexer. And so 19 TPS, but if you throw 5 machines, 5 GPUs, then you're almost at 100 already, right? So the path of FHE scaling is just better hardware, and following Moore's law, this will be a solved problem.
And the user doesn't need to do anything, right? Like, do they need to create client proofs as well, or because their hardware wouldn't help?
So on the client side, so basically, yeah, I think that's another point I wanted to make earlier. You made a good point. So basically, in the ZK system, you have the user generate the proofs, and it's actually quite scalable because millions of users can just generate off chain and then cast it on chain. In the encryption-based system, you have the blockchain itself to do state transitions on behalf of everyone. So scaling does matter quite a bit. But on the other hand, like I'll say, like the ZK proof for a ciphertext is pretty quick. It's not that heavy. And I would say the blockchain itself does most of the work for the state transitions here. Yeah.
Thank you.
Great. Yeah. Let's talk about hardware acceleration. On the last note, before we wrap up, I'd love if everyone could go through and quickly talk about either like one specific use case or set of use cases you're most excited about for the respective PET, and like why that respective PET fits it so well. Let's start with Yannick.
So I think the use case that I would be most excited about, pinning it down to one single use case, I feel like I've been just so impressed what we were able to facilitate on just the sheer number of data and complexity of operations when running fully confidential machine learning, and basically building end-to-end encrypted AI. So having fully confidential training, having encrypted model weights, and then running confidential inference into those encrypted weights. I feel like that's super exciting, and it mostly, I would say, for me personally, serves sort of as a benchmark. Just seeing the ability, how efficient we are able to run those large-scale computations, and that really shows that with our tech, we are able to also then do confidential DeFi very efficiently, since we are able to have those highly complex use cases like AI in a fully confidential way.
It's very cool. For ours, something that specifically excites me a lot is uncollateralized lending. You don't see this in blockchains today because there's so many problems you have to solve. You have to solve the identity issue, then you have to solve the Sybil resistance issue, then you have to solve the credit score issue, then you can get into the lending. Whereas if you have privacy, you can do things like you have ZK email now, which is this great thing of like, okay, you have something on an email, you can prove it verifiably on chain that like this is what the email said. Your credit score typically comes from an email or TLS notary. Boom, done. You solved the credit score issue. Completely privately, so I now know your credit score range without knowing A, who you are, B, what's your credit score actually. Great. Second, you can have a similar mechanism to have identity or Sybil resistance. Credit scores have Sybil resistance baked in. One person only has one credit score. If you create a new address, you'll still have the same credit score. It doesn't matter. And so you've solved all these three issues using one primitive that's already out there. And the only thing, and like all you need to do is just have a normal lending that can be completely public. You still hide everything about the user that you want to, and the user gets like literally a private loan of whatever assets they want. I met a team, it's a stealth team, but they are trying to do lending where you have the borrowed assets straight into your bank. You combine that with uncollateralized lending in crypto, and you have some really cool things. So for the first time, you can have crypto bonds. Currently in crypto, everyone has a labs entity and a foundation entity. And it works because the foundation entity has a lot of tokens, and we're so young that we haven't ever seen a foundation go bankrupt, right? But at some point, people want, like companies want to grow more, they always take a loan. And like this whole idea of taking a loan by putting more money is kind of stupid. Like if I have money, why do I need to take more loan? Only for tax reasons, that's it. So like uncollateralized loan is something that's fundamentally needed to actually make DeFi grow. And I think privacy actually enables all of that.
Okay, so like what do I want to see get used? In general, I want to see like all the gadgets being used, like basically, like even for us, we kind of like build TE systems, but we also use like zero knowledge proofs to actually kind of like proof off-chain the attestation report so that the verification on-chain is really cheap. We make use of MPC to do like key management and stuff like that to enable TE. But if you ask me like specifically, what do I want to see TE being used for, like moving forward in the future, I would actually say provenance, especially in this like AI super intelligence, like we are moving towards this direction, right? But kind of like that aside, how cool it is if every one of us, whenever we generate a piece of data, will actually sign over it, which actually means that like, you know, there's the issue of like Sybil resistance and stuff like that, right? If we can make sure that everyone, let's say whenever I say something or I write something or I take a picture or I play a game, I would always like use my own private key and I sign whatever output that I have. It actually means that all the data that we are processing, we can actually trace it to a source. We can know whether that's, is it from a human? Is it from a machine? Is it from some particular AI model? And this actually, I feel, forms the kind of like basis of our societal trust. Like when I'm speaking to Rahul, for example, I know I'm speaking to him and like there's a provenance, the things that he says from him. But the problem is, I don't think we can force everyone to do that, right? And people might actually lie. They might use someone else might say that, hey, I'm the one that says this, or I'm the one that draws this. Plagiarism exists. What if we can actually make use of TEs or like hardware root of trust in general to actually make this kind of like, to perform the signing on behalf of the user, to force this kind of like provenance chain. Yeah.
Do you ever think about what one-shot signatures would change in all of this?
Yes. So
actually, does everyone know what one-shot signatures are? Quantum computing thing, not at all practical today, but you can only use a key to sign once, and after that, the key is destroyed. So you could never double spend. Changes consensus, for example, where you need consensus because everyone has to agree it's you.
Yes. So actually, one-shot signatures is something that TEs can, well, emulate. So the idea is that if you can accept the trust assumption that a TE provides you, you can actually perform these kind of like one-shot signatures. So all these are like exciting kind of like things that I feel people are underestimating the kind of like capabilities that TEs can bring. It's not just like confidentiality, it's not just like integrity, it's like provenance.
Yeah, for me, I think really just around payments. I think this problem needs to be solved. It's about time. I think based on recent developments, and so for context, we did publish a research paper with Circle Research 2 weeks ago. The reality is this, right? So I actually feel it's really hard to have unstoppable money and anonymity together. Now, what we're trying to propose is something maybe like a little bit more vanilla in the middle where what we provide is confidentiality. And with that, what this really means is that the flow of funds will be traceable, but can handle, I'll say, the vast majority of payments use cases such as payroll, if you want to do B2B payments, if you want to pay to your supply chain. These players are known, and it's okay to basically just hide the amounts. But I do think, today, the reality is we don't have any privacy. Like a lot of the tools that exist today are just very difficult to adopt and also get accepted from a regulatory perspective. So for me, I think payments is definitely, first of all, one of the killer use cases in crypto, right? Everyone uses crypto mostly for payment today, especially using stablecoins. If I send money back home, I shouldn't worry about my parents getting mugged because bad actors can see, okay, some money came to their house, right? And so these are very fundamental things that I think it's about time to really solve this problem for public blockchains. And I think timing-wise, it does make a little bit more sense now, given Tornado Cash happened a few years ago, and then there are, I'll say, alternative solutions, including MPC, including TE, FHE that are encryption-based, that do offer differentiated properties here, and that's making it worthwhile to revisit, basically.
Right. All right, thanks everyone. I think the high-level takeaway for me that was most interesting here is it's easy to kind of analyze each of these PETs in isolation, think about individual trade-offs, use cases, but the areas of overlap, for instance, like both problems that each of them are facing, how use cases are actually deployed are quite interesting, and it's quite messy when you really zoom out and look at how all of them interact with each other, which is quite interesting. But let's get a round of applause for our panelists. Thanks, everyone.